Okay, better? Well, thanks. As I get started, I wanted to just acknowledge several individuals. First of all the work I'm going to be talking about today was funded by the FRA. Also want to acknowledge my colleague, Dr. Terry Beck. We've worked together for about 22 years. And most of the things I'm going to talk about, he was a direct collaborator with. And also I wanted to acknowledge there's been many, many graduate and undergraduate students that came through Kansas State that contributed to the work that I have the privilege of presenting today. And then finally, Ryan Bentman and Jason Johnson are two employees at my company at Cam alluded to. And so I'm going to be presenting some of the work that they did as well. And I wanted to clarify something right off the bat, that if you hear me say anytime throughout my presentation that we did something, it could mean that there were students working into the wee hours of the morning actually getting it done. So just an overview of the talk. To really understand the place of larger diameter wires, we're going to start with the background of the work that we originally started, talk about the systems tests that we developed and the quality control tests that we developed, as well as a new wire indent property, which I call byte per length. That's brought a lot of clarification to the indented wires. And then finally, wrap it up with the new larger diameter pre-stress wire research. So when a pre-stressing wire is manufactured, it goes through, it starts out as a rod, goes through a series of dies. We get the work hardening to get that gives us the high tensile strength. And then at the end of that process, we roll, it goes through 3 indent rollers that create the actual indent profile within it. And this slide shows the indent roller on the left that pushes into the wire, which leaves the indentations shown on the right. And I started working with indented pre-stressed concrete wires back in 2008. And 2011, we got our first FRA project looking at transfer lengths. And at that time, almost all the plants in the United States were using 5.32 millimeter wires, with the exception one plant used an indented strand. And so worked with LB Foster CXT Concrete Ties. They provided 13 different 5.32 millimeter wires from around the world that were used in pretensioned ties. And these all had different indent geometries and different types of indents. And so we wanted to characterize the bond of that. So we created prisms. Prism is just a fancy name for it's a square beam. So it's these were 3.5 inches by 3.5 inches in cross section, and they contain 4 wires that we tensioned to 7,000 pounds. And we could then measure or determine the transfer lengths for those. What we did, we actually cast these prisms end to end. There were 3 at a time, and we actually determined the transfer length at each end of the prisms. There were 6 transfer lengths that were determined for each unique set of wire and concrete. And for the concrete, we varied the release strength, we varied slump, and we had data points. We don't actually measure a transfer length. We determine a transfer length by statistically analyzing the surface strain profile that results when we actually detension. The way we develop surface strain profile, this is one method using a Whittemore gauge, and I'll talk about an automated method a little bit later. But this is a slide I presented, I believe, at the very first rail tie conference in 2012. And we observed there's a very large difference in the transfer lengths that you get with wires having different indent types and geometries. And so for each of these wires, notice there's a range of values. So there's a mean and a range, and we looked at a smooth wire as a baseline. Chevron indented wires are the most prominent. With diamond shaped wires, we looked at spiral and also dot indented wires. So the primary wire requirements are to provide enough bond to the concrete so that the design pre-stress force will be available at the rail seat location, and then not result in longitudinal splitting with the corresponding concrete mixture and the reinforcement edge distance. So we wanted to provide bond, but not produce splitting. The way we typically verify bond plant was we do a rail seat positive test. We actually apply a load at a distance from the end until we get a crack. And we want to verify that if that crack doesn't open up until the value we want, that ensures that at that point we do indeed have the amount of pre-stress force we want. And so oftentimes we talk about the rail seat being 21 inches from the end of the tie. And if we measure a single value, we get a single resulting transfer length. But that's only for that end of that tie. we really need to stop thinking about transfer lengths as a single value, but rather there's a distribution, right? It's a histogram. And we've actually gone out to plants and measured, I think we measured 150 in one day, and you actually calculate a mean and a distribution. And if we were to test these ties in the AREMA test, they're all going to test the same value. Okay. Likewise, if we had a histogram with a longer transfer length, chances are if we tested these ties in a flexural test, we're going to get the exact same result. Even though there's a chance, because there's some tails that exceed 21 inches, but by and large, it's going to test the same. But this stands a risk of some of the ties we produce of not having the moment capacity we want at the rail seat. Likewise, our distribution could be on the short end, which is going to tend to result in higher bursting stresses. And so how do we determine where we are? Well, there are two quality assurance tests that we developed at Kansas State. One is to measure the transfer lengths, and the other is to make sure we don't have a splitting issue. The first one is automated transfer length measurements. This is a photo that was taken at a plant we went to, or as a video. And if this, it was, well, this auto, sorry about that. It's should be playing, I'm not sure. Okay, there it goes across the screen. So this takes automatic, we set that on a tie, and it takes two images captured exactly at the same time as it goes down. We do that, we set that on there on the tie before we detention, and we come back after detensioning, reposition it, and we do image correlation of those pairs, and we come up with a strain profile. And the fact that the strain profile, the top portion kind of bumps up and down a little bit, that's because the ties go in and out. They actually have physical shape. It's not a prismatic tie. So we can actually measure the shape factor, scan the tie, and then correlate back. And this transfer length, in this case, 10.8 inches, that comes out automatically. And so it's a process that we can actually go out and get many transfer lengths at a single time and characterize the bed and see where we are. It's really easy to get shorter transfer lengths. You just leave it in the bed longer. Higher release strengths give you shorter transfer lengths. Unless we actually help one of our clients do that. We looked at the histogram and said, you know what, you really should have a little bit higher release strength if you're going to use that same concrete system and wire type. The other test that we developed, system test, is the AREMA splitting resistance test, and Riley showed a picture of this as well. If we have a tie design that we want to use, that tie design will have a concrete mixture and a release strength and a wire type. We can see, are we at risk of splitting by using the AREMA splitting resistance test? What that does is, for our tie that we want to use, we reduce the edge distance of our reinforcement to from the center of the reinforcement to the edge. We reduce that distance by 25% and make 6 members. They could actually be railroad ties that are shown on the bottom right, or small prisms. We make 6 pieces, which gives us actually 12 ends, but there's actually 24 corner wires. We hold that for 2 weeks indoors. If there's no splitting at that point, then we know we have a 1.8 factor of safety with regard to splitting, because reducing the cover by 25% increases our bursting stress about 80%. So it's a way to tell, do I have a system problem? The quality control tests that we developed to assure the bond quality, the first one is the ASTM A1096 pullout test method, and that was officially adopted by ASTM in 2015. And the second is an automated non-contact wire indent scanner. So the ASTM A1096, this is the cover page for that document. It specifies a pullout test. The pullout test, we actually place the indented wire concentrically in a 4-inch diameter steel can with a special mortar mixture that uses an Ottawa sand and predefined concrete mixture components. We then pull that wire at a rate of 2,000 pounds a minute until we have a slip of 1/10 of an inch at the top of the member. When we did this during the development with the different wire types, we were very pleased that we saw, for each wire type, we saw a pretty big difference in the bond slip behavior. not only do we have a difference, but that difference then correlated back to the transfer lengths that we measured on the prisms. And so for the 5.32 millimeter wires, we had a correlation of the ASTM A1096 test with an R squared of 0.954 with respect to transfer length. And that's simply then we had transfer length as a function of the ASTM pullout value and concrete release strength. Okay, automated non-contact indent scanning. This is version 1 of an indent scanner that we developed. This is actually the first more professional version. We had tabletop things that we had started back in 2011. But what this is, we take an indented wire, we put this in the machine and press a button, and it automatically scans the wire. And we actually take physical measurements of the wire. Here's version 2. It looks very similar. The difference is on a close-up look, we use a more powerful laser, and we've also added a digital microscope to go ahead and capture pictures of the individual indents just for reference. So this is a video of how this actually works. We spin the wire and we're measuring it with the laser. Oops. Go back one, sorry. Okay, run it from this one. Okay, so it's spinning the wire and going down. This is actually about 3 times actual speed. It then goes back and forth and captures pictures because it knows where the indents are. So here's actually what that looks like if we look at the computer view. There where you see the wire rotating on the camera. This actually comes up and now gets the images of that. They're actually not images, they're physical measurements. So for each revolution, we get the laser we're using is a line laser. We get 800 points long, and we're taking 7,200 readings around each revolution. So every 0.05 degrees. So basically, every time we spin it around, we're taking over 5 million individual measurement points of the wire. And now it's being processed automatically. It found the indents. This is all with one touch of a button. It processes it, throws out any part that's not an indent. And now we can come in and compare it with the customer specification. Here's where we're dropping down. And all of the values that we've predefined, it comes in and creates a report. And this is all with just a single scan push of a button. So if we look at this report a little bit more in detail here, there are many things we're measuring. On the column here, we have indent depth, length, sidewall angle, profile area, sidewall length, basin length, width, volume, pitch, sidewall area on the left and right. And so what we have, the left 2 columns, I guess my mouse isn't showing up there. These left 2 columns, there's a low and a high. And so for a customer specification, we can put in if there's a tolerance on depth that's acceptable, or any one of these parameters, we can look at that. We look at these individually by row. There's row 1, row 2, row 3. We report a mean value and also a 5% and 90%, 95% value. So we can put limits on any one of those. And this is just some predefined limits. The white, if we put a -1 in there, it doesn't check it. So when you look at that screen, everything that's green would be in compliance with the requirements. Everything that's blue is on the low side, and anything that's red is on the high side. And this is just putting in some numbers, but that's how quick it comes. When you scan a wire, it's within a minute. You have a full report and you can check with customer specification. So the, oh, thank you. So these 3 are the profiles along an indent, what we call kind of generically the north-south direction. If you think of the longitudinal length of the wire as east-west, these would be the average profile from each row of indents. And you can see a couple things right here where the red dips down. If we looked at that wire would tend to have a flat spot that was rolled in. Okay, it's not perfectly round. There's a flat spot. So when we measure that indent, it actually comes down because the top portion of the non-indented region has dropped down a little bit. Also, the green This particular row of indents, the average, it shows a big skew to one side. So this indent is a lot deeper on one side compared to the other. That means the indent roller is either wearing, or likely we have a bearing starting to go in one of the wheels, or it's not in center. So all this comes out quickly. So this is a unique tool. These are available for purchase through the Technology Deployment Institute that helped do all this. So if anyone's interested, this is fully available now. And the correlation we had with 5.32 millimeter wires, we had an R squared of 0.88. And I'm going to show you the correlation as we take this to different size wires. But one of the things that I mentioned that helped bring a lot of clarity was a new indent parameter that I call byte per length. And so to introduce this, we're going to go back to the original data we had. I'm going to focus on 2 points. One was the smooth wire, which had, and one is this wire WJ. The smooth wire on the left has no indentations, and that had an average transfer length of 15.2 inches. Wire WJ had one of the more average medium depth indent, and that had a transfer length of 9 inches. No surprise, we add indents, we get better bond, we reduce our transfer length. So let's take a look at the smooth wire. That had an average transfer length of 15.2 inches. I mentioned we tensioned these wires individually to 7,000 pounds. So that 7,000 pounds, we divide that by 15.2 inches, we're getting an average bond per length of 460 pounds per inches. And that's primarily due to the Hoyer effect. When we stretch that wire, it gets smaller in diameter. And then when we release it, it wants to get bigger, so it's providing a normal force. And it's based on the frictional characteristics of the wire. Now, if we consider the wire WJ that had a medium depth indent, that transfer length was 9 inches. Well, if we assume it has the same frictional characteristics for the steel, then over that same 9 inches, we get about 4,140 pounds that we could attribute to friction. So the remaining amount, that remaining 2,860 pounds, has to be due to the indents. And on that particular wire with the pitch, the spacing of the indents was 0.221 inches, which means if I take 1 over 0.221, multiply it times 12, I get 54.3 indents per foot in each row. There's 3 rows. So I can convert that to a force per indent then of 23.4 pounds is the force being attributed to each individual indent. I then ask, what would the bearing stress be on that individual indent? So I can take that force and divide that by the depth and the width of the indent, and I get a bearing stress of almost 30,000 PSI. What does that mean? It means the concrete crushes, right? And for the longest time, I started thinking about sidewall angles and get this idea of rigid body sliding, and a shallow sidewall angle is going to have more radial force. And I don't think that's true at all, because the concrete's crushing. And when we crush concrete, it has to be displaced, and it can't go inward, so it goes outward. So the concept of byte per length really is about, we have this material we're crushing and we have to displace it. And I liken that to a snowplow. And if I consider a snowplow has to displace the snow. And if I did something really bad there. I have no idea. Oh, there we go. Okay, a small amount of displacement is not too bad. We have a lot of displacement, that can be problematic, right? So if we have to displace, so what can we do? One of the things is for that snowplow, if we don't want to displace as much material, make it shallower, right? Make our indents less depth. That's one thing. The other thing we could do is, instead of having a rectangular area that's approximate area B times H, we could taper that off at the sides, okay? We'd have half the area. And that's exactly what's done with the European style indents. The European style indents, they have type T2 indent, which is this one right here. And if you look at the profile of this indent, it's essentially the full depth around the whole width of that indent. And so how you see that is on this north and south direction, we see a lip here. So that indent is full height across this depth. The T4 style indent tends to be deep in the middle and taper out. And so we look at that, we have an edge in the middle, and that tapers out. I think that actually is a easier wire to maybe produce and without causing issues, because essentially when you use a T4 style wire, you can withstand almost twice the depth variation than you can with a T2. If you have a depth variation of a T2, it affects that plowing area directly, On the T4 style, you get a factor of 2. So the term that I coined is byte per length. Byte per length is simply the average width of the indent times the average depth divided by the average pitch. And it's a way to quantify the amount of concrete that's being displaced as the wire slips through the concrete. We know in the transfer length, there's relative movement. We can actually measure an end slip of the wires when we detension them. So normal range of byte per length is between about 1 and 20. It's actually units of millimeters squared per inch of length, which people don't like that unit. So I just say it's a relative unit 1 to 20. Otherwise, we're dealing with numbers that are like 10 to the minus third powers or up in the tens of thousands. So if you use millimeters squared per inch, but it's a relative measurement of width times depth over pitch. And so in these same two pictures, the T2 on the left, T4 on the right, the green area would be the byte, and then we divide that by the pitch in and out of the page. And so Steve Mattson at Nortrack and I gave a talk at this conference last year, which was virtual. And if you want to hear from a producer's standpoint, Nortrack used this, the concept of byte per length, and it was very helpful as they looked for a new wire supplier and quantifying a wire. So that's I would plug that if you want some more information. So now let's talk about large diameter indented pre-stressing wires. Everything up to this point was 5.32. And this work was conducted at my own laboratory. It's in Manhattan, Kansas, separate from the university, about 10 miles away. And it's also funded by the FRA, and we had industry partners of Nucor, Nortrack, and Rail One. So our objective was to establish correlation of the two existing wire assessment methods, the pull-out test and the non-contact indent feature extraction, with resulting transfer lengths for larger diameter pre-stressing wires. Because at the time of the original study, I said all the plants were essentially using 5.32 millimeter wires. Since then, Nortrack has used 8 millimeter wires, Rail One used 10.5 millimeter wires. So these various diameters are really being used. They're used worldwide. And so we looked at 8 millimeter wires and 10.5 millimeter wires. For the 8 millimeter wires, we had a smooth as a control. The T4 is the indent that tapers to shallow out of the edges. The T2 is deep all the way across. And we targeted indent depths of 0.02, 0.02 of an inch, all the way up to 0.05 of an inch. For the 10.5 millimeter, we looked again at a smooth, 2 T4s, which would be a shallow one at a depth of 0.04 and a deeper one at 0.08, and 2 of the T2 style indents. And our test plan, pretty much for everything that was 8 millimeter wire, we detentioned at 4,500, half were at 4,500, half were at 7,000 PSI. When we got up to 10.5 millimeter wire, if we want this to work in a railroad tie, it's going to take a higher release strength. Otherwise, our transfer length is too long. So most of our work was focused on 7,000 PSI release strength at detensioning, and one of the wires we looked at 4,500. So the prisms, we used the same shape as K-State, but they had to be bigger to accommodate the wires. And so what we did is we provided the same P over A force. The original prism was 3.5 by 3.5 inches square. That had 28,000 pounds of force in a 3.5 by 3.5, which was about 2,250 PSI was our P over A force. Also, the wires were 1 inch from the center of the wire to the outside, and these were 5.32 millimeter wires. So this distance, the 1 inch, was actually 4.77 times the wire diameter. So we kept those parameters the same. And the strength that the tension the wires to, one of the things I wanted to note, when you go to larger diameter wires, the tensile strengths tend to decrease. For a 5.32 millimeter wire, you can get up around 270 KSI, 275 KSI. When you go to an 8 millimeter wire, you have less reduction of area. So you get 253 KSI is about the maximum that a producer would guarantee. And for 10.5, we're down to about 229 KSI. So by keeping the edge distance at 4.77 times the diameter, we came up with the following prism sizes. For the 8 millimeter wires, the wires were tensioned to 15,769 pounds. They were 5.25 inches square with the 1.5 inch edge distance. And for the 10.5 millimeter wires, each wire was tensioned about 25,000 pounds. There were 6 9/16 by 6 9/16 and a 2 inch edge distance. Additionally, they were 69 inches long, and we installed brass inserts to be able to determine surface strains and transfer lengths. So for the 8mm wires, just a picture of this, you can see the T4 style indent. These kind of feather out. There's no edge on this north and south, only an edge in the middle. This is a T4 depth of 002. Here was a T4 with a depth of 005. We had a smooth wire, and this is a T2 style indent. You notice there's a crisp edge where it's essentially full depth top and bottom. The other thing with the T2, you notice this has a lot tighter pitch. And we did that to be able to explore various byte per lengths. So you can see the pitch of the T4s was a lot longer than the pitch of the T2. There are a lot more edges that are crushing and pushing concrete outward on a T2. For the 10.5mm wire, again, we had two T4s, two T2s. I didn't take a picture of a smooth. I figured you could picture that one. But you can see, again, the T2 style indent, in addition to being deep all the way around, is a lot closer pitch than the T4 style indent. So the byte per length, these varied from 0 all the way up to 16.5 inches. We have a large variation in byte per length. And we did ASTM pullout tests, and we did those with each one. The pullout test is actually an average of 6 individual tests. And so the way the ASTM has you report it is you do 6 tests and you report the value that is the maximum force at an end slip less than or equal to 1/10 of an inch. Well, if I average those curves, just take the average of those 6, these are the results for the 8mm wires. And this is the average pullout curve, and I'm putting the byte per length on each wire. And notice why I'm so excited about this parameter is the byte per length has direct correlation with the bond. The higher the byte per length, the steeper the bond. It works out. So this 0, this is a smooth wire. Smooth wires behave really differently. As soon as we break bond at the top, we're adding tension to this wire. It's not pre-tensioned. So now that wire is trying to get smaller in diameter. So once we have relative movement, the force drops off. But as we add indents, the deeper we go, the more byte we give, the higher the bond. Same thing for the 10.5mm wires. Again, the smooth wire down here. And as we increase byte per length of those wires, the bond increases. So we determine transfer lengths then. There's a picture of the jacking end of the pre-stressing bed that we have. We utilize mechanical gear jacks and a motor with about a 200-to-1 gearbox. And that allows us, we can actually, with a vector drive motor, we can dial in the displacement we want to, I think, one half of 1/10,000th of an inch. So before we tension, we made sure those forces were exactly what we wanted. As Ryan said, oh, we're going to add 20 pounds to that bed that's already at 89,000 and change. He just dials in and you add 20 pounds. It gives incredible control. We actually measure the force of each individual wire using individual load cells. And then at the dead end, we have a load cell that measures the total force. So we have a check and balance between live and dead end. To get the exact edge distances we wanted, we 3D printed the bulkheads. We found that's the best way when we want to get tight tolerances. If you stand in front of a drill press, it's a little bit harder, but we just 3D print the bulkheads. The picture of Jason kind of filling the forms is after we tension the wire, batch the concrete. To make sure we had exactly the right release strength, we have we put a thermocouple in the prism, which is bigger volume than the little 4x8 cylinder that we're going to use for strength. I then developed the software and system. We drive a water bath so that the temperature of the cylinders are exactly slave to the temperature of the beam, and they're usually within a half a degree. So measuring transfer lengths, I mentioned we actually infer transfer length from surface displacement measurements. This is Ryan, is my lab manager. So he's using a Whittemore gauge that automatically logs the data through a Mitutoyo gauge into Excel. He's gone along and taking surface displacements. And again, we get these profiles from which we're looking for how long did it take to fully transfer the pre-stress force. We did this at both initial and after 28 days. And so we're determining transfer length for both. At 28 days, our strain values, these are compressive strains, our strain values grow quite a bit. And that's due to creep and shrinkage, because that concrete begins to keep getting shorter over time. Okay, so here are the results, and we'll look at correlations. With 8mm wire, the smooth wire at 4,500 PSI, we're seeing a transfer length value up around 48 inches. Obviously, that's not going to be any good for a railroad tie, right? But it's a baseline point. If we go from 4,500 to 7,000 PSI, now the transfer length comes down to around 38 inches. And here we go to the T4002, T4004, and then finally the T2 depth indent 004. And so you can get a transfer length here down around 13 inches with an 8mm wire if we just depends on what release strength and what depth we want. Some of the results, I know you can't read this table, but I want to just point out one of the things that was interesting of these wires. This was the 8mm smooth wire, and we had a transfer length of 37 inches on the 8mm smooth. When we went to the 10mm smooth, we have a lot more force on the wire, but the transfer length was only about 23 inches. So why is that? When we have a smooth wire, now that wire is dependent on the surface characteristics, any residual lubricants, any rusting. So when we have a real smooth wiring, a smooth wire, the transfer length is governed by that. As soon as we add indents, then things work much better from a correlation standpoint. So here's the 8mm wires. On the left axis, I have the transfer length times the square root of release strength. And on the horizontal axis, I just have the parameter byte per length. And you can see when we use transfer length times square root of release strength, these two values, these are 2 points, the same wire, different release strengths. That brings our release strengths together. And I just did a parabolic curve fit because I'm not really that good at Excel. That was just a quick and dirty I don't think this comes back up. So Dr. Beck, Terry Beck is doing the correlations in these, but you can see the values come down. And at some point, it appears there's not much decrease in transfer length with increasing byte per length. For the 10.5mm wires, we see kind of the same thing. Again, I'm plotting transfer length times square root of release strength and byte per length. And again, it comes down to a point and almost like forms a horizontal. What's going on there? I think at that point, the wire itself can't grip any more concrete. It's not about adding deeper indents or more indents. There's a flat out shear capacity of that wire. The shear strength of the concrete, it's just going to pull through regardless. Doesn't matter about the indent. So there's a limiting value of byte per length. And anything above that, I think, is just causing issues. So the goal is, can we combine all these results now from K-State, the 5.32mm wires, the 8mm wires, and 10.5mm wires. And my colleague, Dr. Terry Beck, is doing the correlations. And we actually are getting fantastic results. This is correlating with the ASTM pullout value. Now, these we'd expect to be excellent because if there's any changes in the lubricants, we're going to pick that up because we're marrying that with a Portland cement concrete and doing a pullout test. So on the left axis, we have the transfer length divided by the circumference times the force on the wire times square root F prime C. And on the right axis, we have our ASTM A1096 value normalized by multiplying times diameter squared. And there's one outlier here, and this is one of the smooth wires. And so smooth wires in a pullout test dimension, as soon as we start to get slipped, the value drops off. So I'm not too concerned about that because nobody's using smooth wires. If we eliminate that outlier and we can just take all the smooth wires, this R squared correlation goes up to 0.96. And this is encompassing all three different types of wires and many different release strengths. And the dashed lines are just plus or minus 10%. The real test is when you come back to a linear plot. We look at predicted transfer length versus measured transfer length. And I mentioned with this outlier in there, our coefficient of determination is 0.83. If we get rid of our smooth wires, R squared is wonderful. We get rid of all the smooth wires, this goes up to 0.96. So fantastic correlation with 1081s or 1096 values. How about the non-contact indent scan value? We do something similar. On the left axis, we have the transfer length divided by, this could be pi d or diameter. It's basically the linear with diameter times the force times, divided by the diameter times force times square root F prime C. And the x-axis, we just have byte per length times diameter. And R squared is very good, 0.94. You see some of these points are a little bit lying out, and these are the 10.5mm wires and the 8mm wires. And some of that is due to, I think, just the lubricants that are there. The real test, again, is when you take this back to a linear plot, your predicted transfer length versus measured. Here, R squared is 0.77. And I think the reason we don't get as good a correlation is we're not taking into account the surface condition of the wire, the lubricants. Okay, we're only looking at the indents. But 0.77 across that entire body of data with many release strengths, many different diameters, I think is excellent. So I'm really excited about the steps going forward. So what are the new opportunities? We can now apply the understanding of indent geometry and wire size to reliably optimize designs without the risk of splitting. And that's the key. We can reliably do it. And I've talking to some manufacturers, I learned some manufacturers, especially over in Europe, are wanting to go get away from pre-tension ties because of some of the splitting issues and going to post-tensioning. And I think that was primarily due to a lack of understanding. I think you can make pre-tension ties wonderfully because with the tools we now have to understand transfer length, understand splitting, the AREMA test, I think we can do that reliably and with confidence. So why would we want to use a larger diameter wire? Larger diameter wires allow for potentially larger coarse aggregate size. If we don't have other wires as close together, we can get bigger aggregates down. We have bigger aggregates are an advantage for several reasons. We get better aggregate interlock within the tie if we allow bigger aggregates to get through. We have less cement demand. The cement, we have to coat all of our smaller particles. So if we have some bigger aggregates in there, we up our distribution size, we're going to have lower cement demand. Also, we're going to have lower creep and shrinkage. So I think for just from an being able to allow for larger diameter aggregates would be, or larger coarse aggregate. It also allow for to innovate new designs. And Riley alluded to this a little bit, hybrid tie. We've always used one size, one type of reinforcement, and maybe that's a good idea, but perhaps we could look at having ties that typically our need for deep indents is controlled by our rail seat positive, right? Rail seat negative is a lot lower load. Maybe we could use wires with different indent characteristics, perhaps smooth wires, perhaps some debonding. Now that we have an understanding of these parameters, we can actually optimize our designs with confidence. So I'm looking forward to have some ideas here that we're really wanting to pursue at K-State, as well as looking at new tie shapes. We have a 3D printer coming from Israel. Actually just got there, a big Modex. We can print 24-inch by 24-inch by 6 foot long. So we're going to be custom printing some concrete tie shapes and using different size wires with that. Okay, the hybrid tie, getting back to this, what if we had wires that we could allow slippage in the top, but still ensure integrity at the ends, that would allow for more rotational capacity prior to failure. And this I got actually from a student, Josue, that I was sitting in on a presentation that he did a few years ago. And he saw a real advantage to ties that had more rotational capacity in being able to handle fatigue loads in moist environments. So I thought, how do we get that same capacity? That was actually a post-tension system. How do we get that same capacity in a pre-tension system where we don't have all the anchorages? So with that, I came in, I think, a couple minutes under, which is crazy. But if there are any questions, I'd be happy to field those.
Bob, did you do any testing with rust on wire?
In our original study, we did some cleaning of the wires with citric acid. And some of the wires, when we cleaned with citric acid, the bond got improved because we got rid of lubricants. There were some wires that had a rusting, and when we cleaned with citric acid, removed the rust, the bond actually reduced. So rust, it improves bond. It's pretty well documented. A light surface coating of rust will improve bond. And in fact, I think that could be problematic in some product because you're going to have higher bursting demand at the end with wires with rust. We see that in wall panels, in pre-stressed concrete wall panels. They tend to be very thin, and we put a strand in there. Strands that have weathering can produce excessive bursting at the end. But the general thing is it does improve bond.
So to improve variability as best as storage.
Yes. Well, it's controlled environment. However, if you can control the moisture in a certain number of days, it's so many rain days. But if that's a variable, it's best to control as much as you can control. Yes.
The time you're measuring the transfer length of the surface of the slipper of the pipe. Do you think there is a difference if you would measure exactly at the surface of the wire as a relative movement between the wire and the concrete? Because if you are measuring on top, and especially if you have two different transfer strengths of the concrete, there must be a difference between the transfer lengths on top and exactly the wire.
Well, at the in the cavity, the top surface is the only what we can get to. There's been a lot of work at University of Texas with bridge beams, and where they, in fact, one of the ties we actually put vibrating wire gauges down the central axis of a tie, compared the internal strain versus the external. There is a slight shear lag. The internal, you know, there's been a lot of finite element models done for the size member that we're talking about. The shear lag from the center to the outside is probably less than 1.5 inches based on the finite element work that's been done. So I think the fact that in a tie we have wires uniformly dispersed throughout, I think there may be a small effect, but it's going to be very small.
Anyone else? All right, thanks, Don.
Rusty. Oh, we didn't do tensile tests on, well, that's not true. Some of the wires we did, but we did not see an issue with just straight tensile tests. Maybe with fatigue, maybe with where it may get you if you tried to pass a hydrogen embrittlement or stress corrosion. That may be a bigger issue with that stress riser, I think, if you tried to pass a test like that. But I think on the what we looked at bond, we didn't see an issue. And I think the AREMA splitting test is going to, you know, provide the factor of safety against splitting. So I think you could successfully use a T2, and I think many people do, but your tolerance for depth is less than a T4. T4, you're going to accommodate more variation in your depth safely. Sorry.
Splitting of prisms.
We did not have any splitting of the 8 or 10.5 millimeter prisms.